Hello everyone, my name is McEntee, and this summer myself and my colleague Cathal Maguire have been working on a project at the Cinecca HPC facility in Bologna, under the supervision of Professor Salvatore Orlando. Our project utilises the Galileo supercomputer to simulate and visualise supernova explosions in an inhomogeneous ambient environment. Supernova remnants are the outcome of supernova, the highly energetic explosions that signal the death of massive stars. On explosion, the stellar material is ejected from the star and travels freely until it reaches a circumstellar medium. This medium contains the mass loss from the progenitor star in the years leading up to the explosion. When the expanding supernova ejecta interacts with the CSM, some of the material will continue to propagate outward in what is known as the forward shock. Conversely, some of this material will travel backwards into the freely expanding ejecta. This is known as the reverse shock. On the right, you can see a schematic diagram showing the density profile of a spherically symmetric blast wave. Note that this is a 2D slice of our 3D model. Also notice the mixing region where we can see the fingerprint of hydrodynamic instabilities developing. Supernova remnants span for tens of parsec and are observed over thousands of years, with this particular snapshot being taken 1,000 years after explosion. Asymmetries within supernova remnants offer the possibility to probe the physics of supernova engines by providing insight into the anisotropies that occur during the supernova explosion. One such supernova remnant is Cassiopeia A, which exploded approximately 350 years ago and at a distance of 3.4 kiloparsec away from Earth. In this case, asymmetries developed within the blast wave shortly after explosion, while the ambient environment was approximately uniform. Using the Pluto magnetohydrodynamic code, we created dense high-velocity clumps within the initial remnant to mimic the conditions of Cassiopeia A. This next movie charts the evolution of the density profiles of the symmetric blast wave on the left and the asymmetric blast wave on the right over the course of 2,000 years. Notice the development of voids of low density in the asymmetric case on the right. These are produced as a result of the propagation of the initial clumps towards the mixing region. The following 3D model of the asymmetric blast wave at the end of the evolution will hopefully make it easier to visualize the situation. We are clearly able to distinguish between the different regions. And looking inside the remnant, we can see once again the voids of low density, a key feature which is present in Cassiopeia A. This model is publicly available to view and download on Sketchfab, a platform for sharing 3D models. It can also be viewed through a virtual reality headset.
As my colleague Sean just mentioned, this project takes a look at inhomogeneities and anisotropies in supernova explosions and their effect on the evolution of the morphology or shape of the subsequent supernova remnants. While Sean investigated the morphological effects of inhomogeneities or clumps within the initial blast wave, I examined asymmetries in the supernova's surrounding environment. One such supernova which shows a clear region of high density in the surrounding environment is SN 1987A, shown here. SN 1987A is a supernova located approximately 51 parsecs or 168,000 light-years away. It was the first supernova which astronomers could study in great detail, as it was the brightest and nearest supernova to Earth in almost 400 years. Images of SN 1987A show strong interaction of the blasted ejecta with a ring or torus of material ejected into its surrounding environment by the progenitor approximately 20,000 years before the supernova explosion. This is an example of how the morphology and evolution of a supernova remnant can be heavily affected by its surrounding environment. In order to simulate and ultimately examine these effects, I introduced two inhomogeneous features of high density in the surrounding ambient environment. These features included a torus or donut encircling the blast wave, such as that present in SN 1987A. As well as this torus feature, I also introduced a molecular cloud of high density, offset from the origin of the blast wave. The simulation, which utilized the Pluto code for astrophysical modeling, showed the evolution of the blast wave for approximately 2,000 years after the initial explosion. This evolution and its effects on the remnant's morphology is clearly seen in this brief video. This video shows two slices of the three-dimensional density profile of the model, one along the plane of the x-axis and another along the plane of the z-axis. You can see the torus initially in orange and the molecular cloud initially in green. From the previous video, I can imagine it is quite difficult to visualize the final three-dimensional structure of my remnant. Therefore, I've also produced a short video orbiting the final morphology of the remnant after approximately 2,000 years. This three-dimensional model is also available for public access via sketchfab.com, where you can investigate and probe further. On behalf of myself and Sean, I would like to thank our supervisor, Professor Salvatore Orlando, as well as all the very helpful staff at Chineka, particularly Massimo Gadassi. I would also like to thank the coordinators of the Summer of HPC 2020 and my fellow participants for your time and patience. As we say in Irish, slán agus beannacht.